forward to watching this talk by Terry Tao.
Okay, so P1 is 2, P2 is 3, and so forth.
Euclid's theorem.
Okay, so we can look at prime gaps, which is just the difference between one prime and the next. Okay, given one prime Pn, how long do you have to advance before you see the next
plus
prime?
one.
Okay, so the
so
first prime gap is 1. After that, they're all even numbers because all primes are odd after 2. So
sure.
the prime gap starts at 1, and then you have 2, 2, 4, and so forth.
Oh, yeah.
And so you have the sequence of even numbers. And you can ask two basic questions about this prime gap. Okay, so one is how small can this prime gap be in terms of n for large n, and how large?
Over large.
Okay, so
right.
Almost the most basic questions you can ask.
We know it can be 1 or 2.
And in both of these questions, we have a conjecture, which looks impossible to solve by our current methods, but we also have progress. And in both cases, actually, we have progress in the last 2 years, where there's nice symmetry, actually.
That's really recent.
And ultimately, as it turns out, we actually use the same method to attack both questions, which was not obvious, actually, when we started this.
That's interesting.
Okay, so I'll start with the
first
method. Question. Okay, so the basic conjecture here is one that most of you probably know, is the twin prime conjecture.
Yeah, I haven't heard of that before. I'll have to look it up some.
But there are infinitely many prime twins, infinitely many pairs of primes that are distance 2 apart. So another way of saying that is that the prime gap is equal to 2 infinitely often.
Oh yeah, so you said this before about the Pn plus 1 and Pn.
Okay. As you go out into the primes, we know the primes do get sparser and sparser. So on the average, the prime gap actually increases roughly like the logarithm of the primes, actually. But we still expect every so often, just by pure chance, basically, the prime gap should every now and then return back to be as small as it can be, which is 2. Remember, it has to be even. Okay, so this is still open.
It's
this
was
first explicitly posed
just the
by
time.
Polignac in
all the rest of the time
something.
it's even.
And it's still open. For a long time, it was basically just seen as completely out of reach. But we had this amazing breakthrough by Yitang Zhang last year.
To check out some more of the history of this problem.
And the precise date is actually May 14th, 2013.
It's so cool.
We, for the first time, managed
exactly
to get a bound which looks like this. What he showed was that the prime gap is bounded infinitely often. And the bound, he even got an explicit bound, pretty large, but explicit.
Oh, what a crazy number. I wonder what that's all about.
Okay, that there are infinitely many pairs of adjacent primes whose distance between each other is not 2, well, could be 2, but is certainly bounded by some large but fixed constant. So this is the first bound of this type. So previously, the best bound
small,
like this,
but it could be 2, but maybe not. There's this logarithm again.
One could get a bound which is basically a square root of the logarithm infinitely often.
Same as logarithm as before. What's all this going on? It's pretty small.
About 10 years ago. Okay, but this was the first actual bound. So this was an amazing result. It's now published in the Annals of Mathematics. It's amazing for several reasons. Partly because of Yitang's life story. He was an assistant professor in the University of New Hampshire, who actually hadn't published for a while and even left academia for a while, but still was working on this problem and actually solved it and wrote completely correct proof. So there's nothing too special about this number 70 million. It's what came out of Yitang's argument, and he wasn't completely careful. His goal was not to get the sharpest possible number, just to get a nice round number which was large enough for everything that he wanted to do. And so, a large prime gap is the same thing as a big long string of composite numbers. Okay, if you have a whole bunch of composite numbers, then the prime before and prime first prime
that's
to the left of that string.
Right, the number is not prime, so it has multiple factors.
So one of the first things you can prove, and this is something that you sometimes even see in high school, is that the prime gap can be infinitely large. So this gap can be arbitrarily large, and there's a very simple proof. Given any number n, you take its factorial.
What is the main question?
And you look at this consecutive string of numbers.
Oh, we care about it. Not how big
all the numbers from n factorial
one
plus
gap can be, but
n factorial
how
n
often it happens too.
Okay, and these are all composite numbers because this guy is a multiple of 2, which is bigger than 2, so it's composite. This guy's a multiple of 3, which is bigger than 3, so it's composite, and so forth. So you've got this whole string of composite numbers of
because
length,
if you're bigger than
n
3
1,
and you...
So that means that,
I need to work out this calculation.
Right of this string must have a gap.
Yeah, okay, that's an
1,
even number. That's a multiple of 3.
And n can be as big as you want. So the prime gaps can be as big as you want.
Okay.
Now, we can do better than that by using some slightly more advanced technology.
Okay, maybe not right now. I'll come back.
So, okay, so one of the first basic theorems that we can prove about the primes, maybe the most important theorem about the primes, really, is the prime number theorem proven in 1890-something. I should know this.
Okay,
I think
that's another one that I should look up.
Okay, so the prime number theorem tells you roughly how many primes there are up to any given level. So it tells you that the number of primes up to a large number x is roughly x1 log x.
A logarithm again. It must be
log of x. Okay, and
really important.
You actually have to multiply by a little error, which goes to 0 in a relative sense. So
I'm not sure what this.
The ratio between the
little
primes of x and x over log x goes to 1 as x goes to infinity.
I'll have to ask somebody about that.
So for a large number x like a trillion, the number of primes up to a trillion is roughly a trillion over natural log of a trillion. So that's how many primes there are in this interval.
That's so
and so
weird.
Just from the pigeonhole principle.
The pigeonhole principle. I think I remember that from before about.
Okay, what this tells you is that among the primes, among the primes up to x, there is at least one prime gap. That's Pn, which is bigger than log x.
I think I know what the pigeonhole principle is, but it's not clear to me.
Okay. Another way of saying that is that is an equivalent way. Is that the prime gap can be as big as
I feel a little lost.
Small factor times log Pn. The prime gap can be as big as the logarithm of the prime, of say the first prime, infinitely often. Okay, so this is an easy consequence of the prime number theorem and the pigeonhole principle. Okay.
There's
so
something to unpack there, but
okay, can you
least
do
we
any
get
better?
some kind of bound.
The prime gaps be any bigger than this?
Infinitely often.
So we
in
don't
a
actually
growing
know
kind of way.
so much about how big the prime gap can be. I think the best unconditional bound we know is that the prime gaps are always at most a constant times Pn to the 0.55. This is so they can't be incredibly huge. Like
what
they
does
can't be
the
bigger
decimal power mean again?
0.5.
Right, if it's like 0.5, that's
almost the square root of Pn.
Square, right.
This is a
square
theorem
root. Cool.
of Hoysel. No, Baker, Hammond, and Pence. This one. Okay, but if you assume the Riemann hypothesis,
I don't know what that is. Okay.
We know that this.
Maybe it's not
you can
so
put this
important.
to Pn to the 1/2, I think times log Pn.
So what's the first one?
0.55. Yes. Yes. It's just a numerical constant coming from optimizing all kinds of other things. But if you assume the Riemann hypothesis, we can bound the prime gap up to the square root of Pn, basically. But that's still quite far from this pigeonhole. And this is not expected to be the truth. But this is just the best we can do, even assuming this very heavy machinery here, which is the Riemann hypothesis. So the conjecture that everyone believes is due to Kramer. So he introduced a random model of the primes. So he modeled the primes. So the primes up to x.
That sounds like an interesting
just some set
idea.
of numbers up to x. Okay, and we know how many numbers there are.
But how could?
But of course, knowing the
primes
number,
are what they
the
are.
cardinality of a set doesn't tell you everything about the set.
But like
it
it's
just tells you its
random.
distribution.
That's so weird.
So Kramer had the idea. Well, let's pretend that
I need to think about that. Somewhere.
this set we know is cardinality. Let's pretend that it looks random. So he modeled the primes by a random subset. Of numbers up to x of the same cardinality, of cardinality approximately x over log x. So in a way, it sort of giving up on the question of what patterns there are in the primes. Let's say,
Seems like
I don't understand
cardinality is
primes,
maybe
let's
how
believe
many
it's
there
a
are,
random
but I
set.
need to
Of course, the primes themselves
get
are
more
not actually
clear on what
random.
that
You don't
means.
have to roll any die of flipping
Yeah,
coins
yeah.
to create the
Right. I'm glad he's
prime
saying
numbers.
this about random.
The modern way of thinking of Cramer's model is to say that the primes behave pseudo-randomly, that they behave like a random set, even though they're not exactly random. Now, the reason you want to do this is because
All right,
we have
that's
this,
another word to look up,
probability fields are
pseudo-random.
very good at computing what happens to random sets. And we can compute all kinds of statistics of random sets. So, for example, if you take a random set of numbers up to x of this cardinality, you will find a lot of twins, a lot of pairs of numbers 2 apart, quite a lot, actually.
That would be good.
And so
Yeah.
this gives you
That's
some
the kind of
evidence,
thing that we're
some
looking for.
heuristic evidence that twin prime conjecture is true. If you take this random subset and you look at gaps between now these sort of fake primes, these sort of random model of the primes, what you find is that the prime gaps are now this random variable. They'll be distributed like a Poisson random variable whose sorry, an exponential random variable.
Yeah, more things to look up.
The set looks like a Poisson process, but the gaps
Poisson.
have this exponential variable of mean log x. And so you can get gaps larger than log x, but they get exponentially
This random
rarer.
stuff isn't what I was expecting.
As
Talk
you get
about
bigger and bigger.
prime numbers.
And by computing the random,
But I guess that's
by
something
computing,
new that I know now.
the random
But that's
model,
statistics
Kramer's
is kind of
conjecture
important in number theory. That's
that the
pretty
correct
crazy.
size of the gap should be log p n squared.
How does that compare to what he was saying before? Oh, it was like log.
Okay, that if you make
and
a
now we're
especially
squaring.
for a small constant c, for especially small c.
If we're squaring, it should
Okay.
log
If
so
you make a
small,
constant c
but
small enough, you should have gaps
I
that are as
guess
large as the square of the logarithm.
if it
infinitely
gets
often.
big,
But then he also conjectured
squaring
that
will
if you
make it
make the
bigger.
constant big, this should only happen finitely often.
okay. So that means it's there's got to be a
Actually, maybe he didn't quite conjecture
sort
that.
of
But
a just right
this is what the
value.
this is what
Like,
the same model would
can't we
predict.
figure out why it's exactly
Okay, the
right?
largest gap should be roughly of the order of log squared. Okay, you should get an extra log over what the basic equational principle gives you. Okay, but
That was really interesting.